Hello again, welcome to another great video. So for this particular video, we'll be focusing on a past paper from November 2018. So it had two questions that were actually dealing with electrostatics. It was question 9 and 10, so we will do both of them in this example. So let's start with question 9. Right, in this problem we are told that we have a small isolated sphere A, right? And it has a mass. Remember, once something has a mass, it means ultimately or automatically, whichever way you might want to think about it, it means that gravity will act on that thing, right? So there'll be a force of gravity that will be exerted on that object. So now it is carrying a charge of 7 times 10 to the power minus 9 coulombs, 7 nanocoulombs, which is positive, right? And then it is held by a string of negligible mass, and then there's a second sphere after that carrying a charge of minus 8. So this scenario sort of makes sense. You see that sphere A is sort of being pulled towards sphere B. There's even an angle between the string connecting sphere A and the surface, whatever black surface that is, or a ceiling rather, at a 20-degree angle. That shows us that sphere A is being pulled towards sphere B. Now, we're also given the distance between the two centers of the sphere, right? So everything is also in the diagram. And then we are told that we must state Coulomb's law in words, right? Now, one thing that we should also note is it was never specified that these things are moving or not. So we can assume that they are stationary, both of them. They are not moving. So all forces here are balanced. There's no force greater than another one. Everything is just balanced. All right, so we have that. We are asked to state Coulomb's law in words for 9.1. So we know that the magnitude of the electrostatic force, so we say F, is directly proportional between 2 point charges, is directly proportional to the product of their charges, Q1, Q2, but inversely proportional to the square of the distance between them. So that's essentially what Coulomb's law states. So now we go to 9.2. Draw a vector diagram of the forces acting on sphere A, right? Indicates at least one angle. Remember, so the vector diagram, it essentially means we need to just draw a free body diagram. So this is sphere A. I'll draw it as a dot. And we are told to indicate at least one angle. Right, on sphere A, because it has a string, there will be tension that side. Force of tension. We can call it T. Right. That's sphere A. And then sphere A also experiences a force of attraction due to the presence of sphere B. So let's call this F. Right. And then lastly, sphere A experiences gravitational force because it has a mass. So let's call this W, which is weight. Some people prefer to call it Fg. It's the same thing. Right, so these are the forces that we have. Remember, we were told to indicate at least one angle. So we can put it here if we want. Our 20 degrees. Why am I putting it there? It's the same thing. I won't put it here because it's more convenient for me to put it there. I won't put it here instead, but you can do that if you want. But it's just for convenience. Also, the reason it's legal, it's perfectly fine for me to do that. If you remember, if you have two parallel lines, the alternate angles are equal. That's what I did here. I just draw a parallel line to this dotted line here, and I put 20 there. It's the same thing, really. You don't have to worry much about it. So that's what we have right now. Okay, so you would get your marks. They would give you 1 for the angle and 3 for all these forces, all 3 forces. Then you have your 4 marks. Now let's go to 9.3. Calculate the magnitude of the electrostatic force that sphere B exerts on sphere A. Alright, we can find that. We know that if the electrostatic force is equal to K, Q1, Q2, or QA, QB. If we want, we can just say QA, QB. That's still fine. All this over R squared. Right, so now we substitute the values. Alright, so we can write it as QA, QB. And then we can substitute our values. For K, we have 9 to the power 9, 9 times 10 to the power 9. For Q1, or QA rather, we have 7 times 10. Then for QB, we have 8 times 10 to the power minus 9 as well. So notice that we never include the signs, that we just take the magnitude of the charges, not the signs. You don't care about the signs when you're calculating the force. Okay, but you must be able to interpret your answer nonetheless. So the distance between these two is 3 centimeters. So that's 0.03 meters. Then we can find our value for our answer. So I get 5.6 times 10 to the power minus 4 newtons. So in some instances, you may be required to specify the direction of the force, because force is a vector. Actually, it's not even a matter of in some instances. So in this case, they said the electrostatic force that sphere B exerts on sphere A. So we are looking at things from the perspective of sphere B. So sphere B will exert a force of attraction on sphere A, and that force will be towards B. So it will be pulling A towards itself. So we can say right, or attraction. Let's just say attraction. Okay, so this is how you would calculate the magnitude of the electrostatic force between sphere A and B. Now they want us to find the magnitude of the tension force in the string. Right. So if you check our free body diagram, that's 9.4. Let me just copy it as it is. Right, let's put it here. So the diagonal force, or rather the tension T, will have components. You will get a parallel component, right, T parallel, and then you get a vertical component, T perpendicular, or some prefer to call it, this can be Ty because it's in the Y, and this can be Tx because it's in the x. Actually, let's call them that. It makes more sense. Ty, then this is Tx. Right, so you'll have these two components, and then we know that for A to remain stationary, right? For A to remain stationary, the forces must be balanced. So Tx must be equal to F, right? And then Ty must be equals to, and Ty must be equals to the weight. So that's how the forces will be balanced. We can use any of these expressions, Ty or Tx, to then find our tension in the string. Let's use Tx because we just calculated our excuse me, we just calculated our force. So we can say Tx is equals to F. Then Tx is the same as T, which is the diagonal force there, sine 20 degrees. Then we can find T by simply saying, or let's substitute F as well. Right? Therefore, T is 5.6 . So I get 1.64 times 10 newtons times 10 to the power minus 3 newton. So for your own homework, or just to test yourself, try use Ty to find what the tension force in the string is. Okay, so this question had question 10 as well, or this paper rather had question 10 as well. Let's move to question 10. All right, so now for question 10 of this paper, this past paper, we had this problem. So 2 points, P and T, so these are points, they're not charges, okay, are situated 3 millimeters apart in the electric field of positive charge Q. Okay, now we're asked to draw the electric field pattern around charge Q. If you remember, that one is as simple as you just draw, right? You put your positive charge and then you start drawing your lines. Right? And since it is a positively charged sphere, the arrows are going out. So this is what the electric field will look like for a positively charged point charge or sphere or whatever object that is. Right, so 10.1 was a straightforward one. Let's go to 10.2. So for 10.2, the magnitude of the electric field at point P is this, we're given. Okay, we're just given the magnitude. And at point C, the magnitude is 2.5 times 10 to the power 5. All right. So we are given these two values, the magnitude. So we know that this, we can call it EP, the electric field at point P, and this we can call it ET, the electric field at point T, if we want. All right, so let's see what the question wants. The ratio of, or calculate the ratio of the electric field at point P to the electric field at point T, right? The answer is EP is to ET. Okay, that's interesting. So EP is to ET, right? So the ratio, if you remember in grade 3, you would have EP, we said, is 4 times 10 to the 6 is 2.5 times 10 to the 5. Remember, when you're finding a ratio, you take the smallest number between the two and you divide everything. So the ratio would be so you divide this side by 2.5 times 10 to the 5, this side by 2.5 times 10 to the power 5, right? And then now you want to find your ratio. So it'll be 2, 1, obviously, because these are the same, so they just divide. So some people say they cancel out. It's the same thing. Mathematically, it makes no sense to cancel, but much sense to just divide. So I get that this is 16. So this right here is your answer. The ratio is 16 is to 1. That's how you find a ratio. That's a very interesting question for grade 11. Interesting. Okay, so 10.2.2. Now, what is the distance between charge Q and point P? Interesting. All right, so before we move on to 10.2.2, what this means, what this ratio we just calculated, what it means that ET is 16 times EP. So the way you would represent it mathematically is that EP is 16 times ET. So that's what it means, right? So keep this in mind. That's what the ratio means in another expressed as an equation, right? All right, so we can start with that actually and say we know from 10.2.1 that EP is 16 times ET, because when we took 2.5 and divided it into 4, that's like 2.5 to the power times 10 to the power 5, and we divided it to 4 million, we got that it goes there 16 times. So that means ET is 16 times EP, right? So this is basically what it means mathematically in equation form. So now let's try to find EP. We can go and say EP, say 16 times ET, right? Then let's substitute. So let's substitute now. We are looking for, remember, don't lose sight of what we are looking for. We're looking for this distance between Q and P. So let's substitute our values and see if we can find it. Okay. EP will be KQ over R squared, okay, is equal to 16 times KQ over R squared as well. Right. So what can happen here? We can divide both sides by KQ if you check, because KQ is common. So we can, let's say, divide so that means we can say times 1 over KQ. That's dividing by KQ, by the way. Right. And then this will cancel that. This will cancel that as well. Excuse me. And then on the EP side, we can now substitute the value of R squared. Remember, for EP, we don't know R squared. So let's call it X. 1 over X squared. Call it X. Let's call this distance X. right? And then on the side of ET, it looks ugly. Let's just write it as a subscript, not like another letter. We'll have 16 over, we know the distance over, we know the distance from Q to T will be just x plus 3, right? So this will be x plus 3 all squared. Right, you can take the liberty of solving it using quadratic equations and whatnot, but on the other hand, you can simply square this side and square that side. So let me make it its own step. We square both sides. So now we're squaring both sides. Ooh, my bad, I forgot that. This is a very, very crazy mistake. 0.003, not just 3. Right, then same here. Much better. So let's square both sides. So this will remove these squares. So now we'll have 1 over x is equal to 16 over x plus 0.003. From here, you can use your maths and solve. Right, so you can say cross multiply. Let me use arrows. I don't want to write cross multiply. Then you will have x plus 0.03 is equal to 16x. You transpose, then you have 15x is equal to 0.003. Then x, you get your answer to be, I get 0.002 meters. Right, that's my x. It makes sense for my x to be, for this distance between Q and P, to be lower than the distance between Q and T. That's another way to sane check, or to do a sanity check for your answer. Imagine if we got that x is 0.1. That's totally ridiculous because it's greater than the distance from Q to T. So that's impractical. That would tell us that our answer does not make sense. So we likely made a mistake somewhere. But this one, fundamentally, it makes sense. All right, so that's how you would tackle this question. So now let's find the magnitude of charge Q, which is 10.2.3. And then before we do that, one last thing we forgot to do here, which is a very big mistake, was this. This is supposed to be 4 because we put a square root, remember. Square root of 4 is, of 16 is 4. So we must come back here and change this as well. Then this means here we'll have 3x instead. This means we will likely have 0.01 here. Let me just double check that. 0.003. Yes, 0.001. All right, so this is how you would tackle this question. Be very aware of your mistakes as well. Anyone can make them, by the way. But as long as you will be able to go back and check where you might have made a mistake. So let's say we want to find EP. We're going to say KQ over R squared, right? So we're told to find the charge of Q, right? The magnitude of Q. Let's make Q subject of the formula then. So we can say Q is EP times R squared, all this over K. Then we know we're given EP, right? EP is given to be 4 times 10 to the power 6. So we take that, we put it there, right? And we just calculated the distance between Q and P as 0.01. We square that. and then we put our constant there. Right, at grade 11 you should know how to make something subject of the formula from maths, so I hope this part is not confusing. If it is, just go back and revise your mathematics, or do it the way that you would find it easier to solve, because at this point, or this question rather, it was a matter of substitution and then solving thereafter. There was no thought behind it, a lot of thought I mean. So I get 4.44 times 10 to the power minus 10 coulombs. Luckily, or rather fortunately, charge does not have a direction because it's a scalar quantity. So this brings us to a close of, or the end of, this past paper problem. I hope you had fun, or I hope rather you understood what we're trying to teach here. And then thank you very much. I will catch you on our next video.